Welcome to the course Algorithmic Design. Okay, so this is session number 1, introduction lecture. I'll try to explain a little bit what I mean or what we mean when we say algorithmic design. So algorithmic design explores design methodologies which heavily employ data structures and algorithms. And this term is, on the next slide, I will explain a little bit there. There are some different terms that kind of refer maybe to similar things. And very, very broadly, basically, this just means that we are using computers not only to draw or kind of to generate these or create kind of drawings of designs, but basically use them as, I call them here, programmable drawing agents, or so in a way use the computational power of computers and the fact that in a computer everything is represented as data in order to facilitate design, to basically design, or which is very different than how, if you think about it, how design is maybe traditionally done, where you are kind of creating a drawing or maybe creating a model, or so in a way here write about this sort of agency of a computer. And you will see in the presentation I also mention a lot nature, because somehow many of them we are basically using a computer as a laboratory. I'll actually just skip here just quickly. For us, in a way, if you're a scientist, then the role of science is basically to investigate nature, and you perform experiments in the real world. And if you're a computer scientist, you basically, a computer is your laboratory, or the experiments that you perform are in a computer. And there's this kind of idea that with computer just helps you to basically perform computations faster, and it really, in a way, you could also sort of simulate the real world, or by kind of deducing some rules or some maybe observing some principles, how the real world works, and then kind of translating them or abstracting them into the digital world, And so if you're a computer scientist, you basically perform experiments on a computer, and we will be doing that a lot. So we are working in this, and somehow the hope is that even though we are bound to this digital nature of the computer, the lessons that we derive are, of course, relevant for understanding, well, the real world, the universe, and in that sense, design as well. And this is our starting point, so we kind of we will really be using a computer basically as a platform to facilitate design. Okay, and before we dwell any deeper, this is a slide that I just added maybe yesterday, because I realized that the course is called Algorithmic Design, but there are actually many other terms that appear also in the text that I give you, and the way that I kind of introduce the topics, I use many different terms as well. And there's always a kind of a confusion what they mean. And the reason why there's a confusion is because there's no really consensus of what exactly they mean. And depending on the kind of country, the age, or, the person, these terms are kind of, they're used a little bit differently, so I tried to kind of list them here and explain a little bit what they mean. This is, of course, just my viewing of it. So, for example, when we talk about digital design, this is basically design in a way. We are here relating to digital methodologies, but not necessarily computers. And I can't really go deeper into that. But when I say digital, I don't really mean just necessarily related to computers. Digital for me just in a way means this discretized, discrete, relating also in a way to the root of the word, digital, the digit, the kind of finger. So kind of the fact that you can kind of count something, that you have discretized quantities. And then, of course, computers are great because in the computer, everything is represented with sort of zeros and ones, even though these are just kind of, some electronic switches. But then we can perform computation with these discrete quantities. So that's, for me, that's when I say digital design, that's what I mean. Also, it's not necessarily related to computers, even though the way we use it is, of course, usually by using a computer, even though we can talk about digital design completely outside the realm of computers. And you can, of course, you can argue there with me about that. So this could be a good point of discussion, but this is just my position. Then we talk about computational design, and this is actually, I like this term more. And also the manual that I pointed out before is called Mathematical Principles of Computational Design. So this is somehow related to computation, or so design that is facilitated through computation, and computation can be analog or digital. Or so we would, of course, primarily think of again, computational design as being facilitated through a computer, just because it's easier to do computations with the computer. But you can also find many good examples of computational design that are analog. For example, what Gaudi did, so form finding with kind of the this kind of hanging chain models that he used to design Sagrada Familia. This is an example of like analog computation device in a way, and you can do the same thing in a computer. Of course, it's easier to simulate in a computer, but he did it manually because he did it more than 100 years ago, when there were no computers. Or so, computational design relates to computation, which can be analog or digital. And then algorithmic design, which is the name of this course, is related to algorithms and data. Or so, and of course, this is as well related to computation, but here the emphasis is really on really kind of on this data representation of design. Or so when we moved from drawing on paper to basically drawing on a computer, we can of course print our designs on a paper, but they dwell in a sense in a digital realm as data, and that gives us some advantages. Or we can then operate, we can use algorithms to operate on that data directly. And it's it seems like a subtle difference, but it's actually very, very fundamental difference in how we can facilitate design. Okay, and then there's generative design, and this is maybe the most controversial term because it's not really clear what this generative means, especially when you're talking with designers. Maybe when you talk with computer scientists or mathematicians, they have a bit better notion of what generation means. But I would hear always, when I say generative design, for me, this is kind of always related to emergent systems and phenomena. Or so, for example, you know, we work with cellular automation, so cellular automata systems, where you have simple the rules that can be defined in a simple way, but you can get very complex behavior. Or that's an example of an emergent system. And for me, this is in a way maybe would fall into the realm of generative design, and maybe topological optimization would go in there, and so on. And then maybe the easiest term to explain at the very end is parametric design, which is simplest because it's just, so parametric design makes, I wrote here, kind of related to the use of parameters rather than fixed relations and quantities. Or so in a way, you talk about parameters that from which the design is in a way derived, and we make these parameters explicit and operative. Or so we maybe facilitate them through code, or we actualize them through code, and we work with sort of domain of these parameters always operate on some domains, so they can be fixed if we choose so, but we can also look at kind of what does it mean when we look at the kind of whole domain of parameters. Or so I'm not anymore talking about, you know, if I talk about a room or a building, I'm not talking about specific dimensions of the building or the room. I'm talking about this relation that the room can have length and width and height, and these parameters can actually be open. And then depending on these parameters, we can determine what happens inside the building, how the space is subdivided, how the rooms are subdivided, or floors. So there we talk about parameters in a relational way, or rather than kind of rather as fixed terms. And of course, Grasshopper in Rhino is the perfect example of parametric parametric design sort of environment, because it in Grasshopper all these parameters are explicit. They're just sliders, or you can just slide them around. So that maybe that design here is also might be the simplest to explain. Okay, so these are kind of the terms, and as I said, they're a bit controversial. There's no really consensus in the community what exactly which one means. And the text that I gave you, I think there's 60 of them. You will see these terms be defined in a little bit different way. So different authors just refer to them differently. And yeah, just because design is not a precise science, I guess. Okay, so this I already mentioned, kind of computer as a laboratory. So we will use basically as computer to facilitate computation. Okay, and then there's this brings us to another very important part, is that in order to use computers or to use this computational power of computers, so to not just be users, but kind of program our own code and program our own kind of designs, we need to be literate in writing code. So we basically need this digital literacy, which is kind of writing and executing code. Also, and it's so fortunate or unfortunate in a way that in schools we are taught how to kind of read and write. So that's we have this literacy or reading and writing. Then we have numeracy. In the first grade, you as well have math, so we learn how to count and calculate. And but we are not really taught kind of digital literacy, at least not maybe at the very beginning, or maybe this is now, of course, changing. And if you ask me, you cannot do this early enough, or so. So I was, for example, learning it already in elementary school, and then continued in my high school, then started studying architecture, and kind of lost it a little bit, and continued with my master's, and then kind of started coding again. So for my path, it kind of coding came and went, but basically, in order to kind of really delve into this world, we need to be digitally literate. Or so, if you don't know how to do it, that's your first priority. And I will help you here. So we'll start with kind of basic coding, but basically, yeah, the more you know, the better. So we have to kind of work on that. Okay, next one. Okay, and then again, why is this sort of why is this sort of really important for architects or designers in general? It's because it's of course not just designing things on a computer. I mean, you can of course be a web designer or a graphic designer, and you're just suggesting kind of producing sort of web apps, but we are interested in building things in the real world, or at least I personally am interested in building things in the real world. And there's a certain correspondence between this digital data and the kind of physical artifacts, or so we can use computation and data or code to basically create physical artifacts, and through use of digital fabrication. And in this course, we will not really work with digital fabrication, but it will be sort of implicit through everything we do. Or so I will maybe refer to some terms, like I will talk about maybe CNC milling or 3D printing. We'll not really go into these topics deeply in this course, but there's another course that called digital fabrication, where we maybe go a little bit deeper there. So there's a certain correspondence between sort of data and sort of these physical artifacts. Also, we can use data to actually produce these physical artifacts. That's one way of using code. Okay, and then there are certain assumptions that we have to make when we work with algorithmic design. I mentioned this. Okay, certain assumptions, and I will run you now through these assumptions. I call them sort of assumptions and concepts in algorithmic design. So we need to have this strong belief that rules rule the world, and that's basically a scientific paradigm, or that's this paradigm of scientific or material determinism, and in a way scientific reductionism. Or so the world is complex, but it's governed by a finite set of interconnected rules, and these rules themselves are simple, but the consequences of them, of their interactions, are not. And that's, in a way, you can kind of summarize maybe the last 500 years of scientific progress to basically that. Or so there's a belief that there is that we live in a complex world, but somehow, again, the underlying rules are much simpler, and they are maybe expressed through formulas or some simple physical laws that we can discern. And this way of thinking helps us a lot also when we talk about algorithmic design, because that means we can sort of set up really simple rules, simple codes, and we can achieve complexity through that. Or so that's, in a way, we can create sort of emergent systems where complexity kind of emerges from these simple rules. And let me just see. Okay, so there's also another shift a little bit. Well, how these rules are applied, or so. The issue with code is that code is sequential, or at least the traditional code is sequential. So it's basically a text, and it's, in a way, in a computer, it's executed in a sequential way. And here on the bottom, you can see musical score. But of course, it's not hard to see that the world does not really seem to operate like that. Or the question is, what is this sequential? How is this, or it's a bit hard to see, for example, this sequentiality in the real world, or because how would you write a code that describes, for example, a flock of birds? Or because here you have many things that happen at the same time, or so there's somehow inherent parallelism to the world, or many objects that sort of interact. But again, code is sequential. You have kind of, line by line by line. So we have to sort of deal with that, and I will show you some basically tricks how to do it, how to think about the real world, and sort of in that way discretize it through space and time, and make things seem to kind of run in parallel, even though in computer they are executed in a sequential manner. And this is, of course, important when you build up simulations of the real world. When you build up sort of simulations of the real world, you have to kind of be able to make the shift to go sort of from serial thinking into kind of parallel thinking, but again, be able to write it through code. Okay, and in order to do that, there are these kind of few worldviews that you can adopt, and we will work primarily in the object-oriented worldview. So that's, if you heard about object-oriented programming paradigm, that's basically it. Or so this world, well, I could also call it a paradigm here. I just call it the worldview to make it a bit more general. In a way, this worldview means, or kind of implies, that everything is an object, or so everything in the real world can be described through basically objects. And these objects have internal states. It's basically like some data that is internalized in the object, and these we call attributes. And I will also call them, when I create an object, for example, in Python, I will call these these internal states, this information, I will call them attributes of an object. And these attributes can be created, modified, or in a way here destroyed, but just means kind of deleted. And these objects have also internal functions. And these functions I will call methods. I mean, in the object-oriented paradigm, again, these internal functions of an object are called methods. So I'll just try to use the same word. And these methods, they operate on attributes. Also, they are kind of, the world consists of collection of objects that have attributes, that's some internal data, and they have their own internal methods. And these methods are functions, and they operate on attributes either of the same object or of other objects. And in this way, you can actually simulate many things in the real world. Also, it's a very useful way of thinking, even though if you go a little bit deeper into literature, you will see that there's also a lot of critique of this way of thinking. But for example, Python is an object-oriented programming language. C++, Java, and so on. So many of these very popular programming languages are object-oriented. Okay, so it's a very successful paradigm. Here I have they're a bit small, but you can have a look at them maybe also a little bit later. So I can have an object, for example, a circle, and this circle has certain attributes, which could be a radius and center. And I can have another object called rectangle, which also has maybe an origin point and length and width. And these objects, they have a class also. They have a class which kind of describes them, how they look like, and then from this class I can generate different objects, different instances of this object, and maybe they inherit their properties from another object or another class called, for example, shape, because rectangle and circle are sort of shapes. So I can create this hierarchy, and also in design and in architecture specifically, hierarchies are very useful, because here on the bottom you can see I can think of a building as somehow comprised of linear axes, and I can say, okay, there's a center of an axis, but then every axis has a certain profile. So I can kind of apply profile, which is like a cross section, onto an axis in order to get a three-dimensional model. Or so I'm thinking in terms of hierarchies, or that's this object-oriented kind of worldview. And again, we will work with that one a lot, and we'll talk about classes and objects. Okay, there's another worldview or paradigm that you can adopt, which is a function-oriented worldview, where you basically say, well, everything is either a function or a datum, or basically data. And these functions, they don't have internal states, and data also doesn't have internal states. Data is just information, so there's no additional structure to this data. All data is kind of simple. They're just numbers or strings or something. And these functions operate on data. That's it. And data is passed through one function to another function, and we are basically they're just functions. They're kind of data. And for example, so there are functional programming languages for example, Haskell is one of them. And you can look at, for example, computational models like lambda calculus, that is a form of it's a functional computation model. And Grasshopper inherits a little bit from that point of view. So Grasshopper is basically a flow-based programming kind of language. And in Grasshopper, if you ever played with it or worked in it, there are these components which are basically functions, and data comes from left, goes into the function, and it kind of gets spit out on the right. And basically sort of the data kind of goes more or less from the left side of the canvas to the right side of the canvas. So there's this idea that kind of the data sort of flows through these functions. And yeah, so this is basically this functional programming, or kind of functional worldview. And of course, the things are a bit more complicated, because in Grasshopper, the functions are not really pure functions. They, if you go in and you have this C# code or Python code, components can actually, if you go in, you can actually have a kind of object-oriented code inside components, so you can actually combine paradigms in Grasshopper as well as, for example, in Python. So it's not really a pure functional programming language. So not at all, but it's kind of, it strives to be in a way simple, or they kind of have components and data just gets passed, and not only that it's passed, it's basically kind of copied from stage to stage. So you can have kind of a code, and sort of the result is some object, in this case a bicycle wheel. Okay, in this course we will not work with Python too much. We will not work with Grasshopper too much. I'll show you some maybe things that you can combine with Grasshopper, but we'll primarily stick with Python. And maybe we'll do some Python components, but yeah, there's a reason, and I'll explain a little bit why. But kind of Grasshopper is great, but it's very hard to build up on that if you don't know kind of, if you don't know how to kind of code or write code from scratch. So we'll focus on that during this course. It will get you much further. Okay. let's continue because this presentation still has, it's not nearly finished. Okay, then another concept in algorithmic design is what I call principle of opposites, or so in a way that this idea that all tension comes from interaction of opposites. It's a little bit related to maybe Newton's third law, that for every action there's an equal and opposite reaction, and then the whole world is composed of opposites between which there is tension. So we can talk about kind of function opposites. So we can, if I have a function a, then minus a would be sort of the opposite. That is the function that does that undoes what undoes the operation that function a does. You can talk about vectors also. If a is a vector, then minus a is this, it's this inverse vector. Or I can have a list opposites, or I can have a element I in a list, and its opposite is in a way element minus I. So if element I is the first element, the element minus I is the last element in the list. Also, this is of course very useful in languages like, for example, Python, which really tries to use this this maybe simple notation with kind of minus to indicate opposites, or so you can kind of quickly inverse things. Okay, and this leads us a little bit to this to another kind of concept, what I call principle of sameness or state of equilibrium. This kind of recognition that all naturally occurring phenomena can be to some degree described as either states of equilibrium or states which are trying to reach it. Or so we are talking about kind of when you talk about simulation, we're talking about simulating equilibrium states. For example, if you do graphic statics, we talk about kind of big equilibrium states, and we will do dynamic relaxation, which is basically kind of trying to find a minimal surface for a set of constraints, and that's basically also kind of sort of search for equilibrium. And of course here, this principle of opposites also works, or because somehow there are forces and they're trying to kind of equalize each other, or so in a way the second law of thermodynamics, or everything is trying to become the same. The entropy is kind of increasing constantly in a closed system. Okay, a bit kind of, I don't want to throw too many kind of topics at you, but just kind of to point out that there are some there are some concepts there that kind of connect, let's say, computation and computation principles and the real world, or so when you talk about nature. Okay, so these are some examples of real world processes that again could be understood as somehow dynamic processes that are kind of trying to reach this state of equilibrium. So for example, for a seashore or kind of a shoreline, what is actually happening is that the sea is constantly kind of hitting on the rocks, and erosion or sea erosion is basically trying to, you know, in a way mix all the sea and all the earth. Or so that's why kind of the earth is, or the coast is kind of crumbling and falling into the sea, and a little bit of sea is kind of going into the shore. So there's this kind of line, and you know, maybe some equilibrium state is basically everything turning into kind of grain and mixing with water and so on. So there's some interplay of forces there. Of course, atmosphere is basically also that. Also, the temperature is always trying to equalize. That's why we have the wind and so on. But Earth constantly rotates, so real equilibrium is not really possible. Or we have a kind of a dynamic equilibrium when atmosphere and temperature is oscillating and so on. And some of these topics are then related to these concepts of fields, or so that we can have space or fields, which can be two-dimensional or three-dimensional, and we can sort of map certain quantities there, so certain vector quantities there, and this we can use as kind of guide geometry, or so we can use these concepts of sort of fields and equalizing tension in order to create design. Or these are examples from Rowan Mayer's UK-based designer. Okay, and another concept when we talk about algorithmic design is discrete quantities. Also, everything needs to be discretized. So we are discretizing time as well as space. So in a way, being discretized or simulated reality in the computer is not perfect, but it can still be very useful. This is a paraphrase from another source, where kind of the idea is all models are wrong, but some of them are useful. So we're in a way creating a model of reality. Okay, and this discretization is of course inherent to computers. So we cannot really work with continuous quantities, even though we can sort of divide. We can divide this continuum as much as we want, or to let's say an arbitrary precision. So when we talk about images, we talk about pixels. When we talk about sort of shapes, three-dimensional shapes, we always maybe talk about meshes, or we talk about surfaces, edges. In a computer, of course, also even kind of analog signals like sound is discretized. So we would have kind of a sound sampling. And if you do it fine enough, you almost cannot tell the difference. And of course, yeah, in architecture, kind of many things are also discretized. So we can talk about kind of room arrangements or spatial arrangements, and then we can describe them as graphs, which are sort of these discrete models. Also, discretization kind of comes with computation. Okay, or at least with digital computation. Okay. And then there's this nature and culture dichotomy, or so this is a bit, I apologize for being a bit kind of poetic here, but I was once inspired and I wrote this down, and I'm kind of sticking to it. In a way, there's this, we're talking about culture, which is sort of, everything that is produced by humans. And then we are there's kind of nature also. There are kind of natural processes, and we personify this nature, or the things that are created by nature, when the nature is not a person. And in a way, culture can be inspired by nature. And if you look at kind of history of art and architecture and design, this is for sure true, that many times we took inspiration from nature. But I would say kind of the projection into the future is that that it's not that culture is trying to imitate nature, but culture is in a way trying to supersede nature. So it's trying to kind of become even more than the nature itself, kind of a supranature in a way. Okay, so these are some examples of sort of art or architecture kind of trying to imitate nature. And many kind of style periods or artistic kind of architecture periods can be in a way also described as humans' relation to nature, or are we trying to kind of sort of conquer it, or are we trying to sort of maybe a bit more kind of an Eastern sort of Taoist approach kind of coexist with nature. Of course, today these topics are very important because of climate change and sustainable development. Okay, and this kind of very nice examples that I managed to find when I talk about analog computation. Also here, there's a grandma here. This is actually these ornamental lace patterns, or so they're being produced in kind of Mediterranean region. So I come actually originally from Croatia, and this may be an example from Malta, or examples also in like Italy, creating these ornamental laces. And there's this grandma here, and she's basically following an algorithm. Or to create this ornament, you have an algorithm that you're following. So you could basically code this. You could just do it in a computer. And so this grandma, even though she looks like she maybe never sent an email in her life, she kind of operates in an algorithmic way, or she understands that to create a pattern, she needs to follow a certain rules, and these rules can be also very, very complex. And they seem repetitive, but if you look at the lace a little bit closer, you will see that there's also quite a lot of variation. You can see this throughout kind of human history, or where ornamentation was very kind of present. And yeah, there was, I would claim, algorithmic thinking in design way before we had digital computers. Or so that's kind of a little bit related to the beginning when I said, when I talk about computational design, I don't really mean necessarily computers. This part is called morphogenic principles, which are not really related to morphogenesis, but somehow at one moment my way of talking about trying to kind of see what are these sort of basic principles that we can use in order to shape things or to create form. And of course, this is related a little bit to modeling, but also to kind of computation and how we can work with code and code shapes. So one of the principles is growth. Or so in a way, entities are regarded as agents which can propagate, procreate, and die. So we really talk about kind of growth patterns, and it's clear that in nature, basically everything is grown, or so everything that nature creates, all the kind of organic life is somehow grown, or you start from maybe a single cell and you go on from there into a whole organism. And how this happens is not really well understood yet, and I think there's going to be many more decades of research needed before we understand how even these processes work. But some basic principles we can extract. Or so, for example, we know that many tissues in our body are fractal; they have fractal structure, and we will be looking at some of the fractals also later in this course. So, okay, fractals, you know. And this is related to optimization, to kind of packing a large exchange surface area in a small volume. So that's how you kind of get lungs. But in this case, these are actually, these are lungs, but similarly works in kidneys and so on. So there are some principles that you can kind of use to read then how this growth maybe happens, even though we don't really know in detail how it actually happens, how it's actually facilitated. It's way too complex yet, or complex, but it's not the goal. The goal is kind of to peer and try to find some kind of underlying principles that that can sort of help us, generate form basically in a computer. Okay, subdivision is one other method. So in a way, you can subdivide. So these entities or objects, you can subdivide them into other self-similar objects, and we'll be looking also at subdivision, specifically of kind of meshes. But it's again clear that in nature, many things are sort of subdivided. So tissues, cells, and these are some of the, I think, sea creatures. Some examples from there. Then layering can also be used as a technique. So you are kind of just layer, you kind of put a layer on top of layer on top of layer, and that way you can kind of create maybe volumes or shapes. And this is maybe the principle that we will look at are sort of metabols, or sort of modeling with these so-called functional surfaces, and it's a bit related to the field concept. So some, again, basic principles there, we also know how they work, so we can actually simulate them in a computer. But this is an example of a tree section, or where kind of every year another kind of layer is sort of added, and here we even have sort of two cores that sort of merge. Okay, subtraction. In a way, we can create forms by carving out, so subtracting, removing. So we have kind of a full form, and then we start removing. And this is, of course, how sculpting is being done. So sculpting, so making sculptures in stone is being done. You have kind of a block of marble, maybe, or stone, and you just subtract all the small pieces. What Michelangelo said, I just removed the little pieces in between. The statue was always there. I think it was Michelangelo. I hope I'm not misquoting. Okay, so we can kind of subtract, and of course in nature, this is also how erosion works. Or so you have kind of layers of maybe earth and rock, mountains, and then through erosion processes, they are kind of slowly, material is slowly being removed. That's a little bit again related to this second law of thermodynamics, that everything is trying to kind of, the entropy is increasing, and in a way the world is tending towards sameness, or tending toward kind of everything becoming dust and kind of completely mixed throughout. Okay, and this distribution also, once we can sort of add, we can so layering is related to addition, subtraction is or erosion is related to subtracting, so removing, and then we also have distribution. So when we already have a fixed amount of material or elements, we can just move them around and put them in different configurations. So that's also one way of creating form and shape. And in that sense, that's, for example, how the sand dunes are formed. Also, the sand is already there, it's just being moved around. Okay, and then the deformation. There's also a text here on the bottom left. There's a reference from Darcy Thompson. It's actually already 104 years old text. It's incredible that the text that old is still relevant, and we actually have it in the extended readings. You can go and have a look at it. This one kind of excerpt from his book on growth and form. Thompson was kind of looking into, he was an evolutionary biologist, and he was basically trying to see how you can create all this variety of life or life forms. And he figured out that many of them can be explained through simple linear or non-linear transformations. So for example, these are affine transformations here, and these are, for example, non-linear transformations. So that's at least kind of how, in this case, profiles of fish can be sort of, so you can kind of stretch them around. And in, for example, Rhino, in the kind of 3D modeling environment, we can use similar techniques to kind of deform objects. For example, cage and cage edit can be used very easily to sort of deform objects. Also, we can kind of deform objects as well to create sort of new shapes or new objects. Okay, and this is just a collection of some of these. So these are all the sort of principles that, in a very, very reduced or abstracted form, that nature is using. Some more tree sections, and yeah, we can use them in that sense to create. I mean, I hate using the word bio-inspired or biomimicry. I really don't like those terms, but in a way, they are kind of organic looking forms, and they look organic because the way that they are designed is maybe, or the principles that we used when we design them are similar to the principles that nature is using as well, when nature and personification, let's say, of nature is sort of designing. That's why they tend to look similar. And the larger story is that these are often related to optimization, or so there's something optimal about these forms. They're an adapted form, or so when we talk about optimization, we can also very often arrive to these shapes kind of automatically. Okay, this is an example. So 3D printing project by Benjamin Dillenberger and Michael Hansmeyer. Some of the students who already took my courses, they probably saw this project, but we also have, there's a text. Again, in the text, you can have a look by the last name. I think it's a paper called Mesh Grammars, where some of these subdivisions are, some subdivision methods are explained. So Benjamin Dillenberger is a professor in Zurich, DTH in Zurich, and he's now leading a group called Digital Building Technologies. So he's basically looking into this cross section between digital fabrication and construction industry. And this was the projects that he did kind of before is basically kind of large scale, super high resolution 3D printing. And he uses subdivision, and actually one of the code that we will look at one moment is a code that comes directly from him or from his group that he was kind of showing to the students, and we can sort of create similarly looking subdivided kind of meshes. And of course, they invested a lot of time to make these shapes actually be producible. Or so it's a bit different. There's a big difference in just generating them on a computer and then being able to fabricate them. Or because if you know a little bit about 3D printing, you know that your meshes need to be kind of closed. So and these subdivided forms are, in a way, bad meshes, or so they don't really. It's very hard to print them unless you have some workarounds. But yeah, that's kind of, I guess, some people invest a lot of time in doing that research as well. Okay, some example from the art world. Agnes Martin, American abstract painter. I actually took her works because in her work she employs a lot of repetition. So it's almost like it's called algorithmic or almost kind of machinic precision. Or it's not really precision. The idea is, for example, these blobs that you hear on the left. The idea is there's hundreds of them, and they all look similar, but they're all a little bit the same. And or sorry, they all look similar, but they're all different. And the reason why they are different is because they're actualized in the real world. So every blob is a little bit different. So there's this interplay between almost machinic repetition and kind of infinite variation, even in the simplest of forms. And this is somehow, well, related a little bit to the kind of the whole process of, it's not a printed, these are not prints. These are sort of like small paintings or graphics. So they're done with the pencil. There's a certain amount of imprecision there. This is maybe even more evident in the works of artists like Jackson Pollock, where the painting is basically, it's all about the process, so it's all about this kind of dripping. Without the dripping, without the kind of the process of, or this choreography of, dance above the painting, you could never get anything similar. So where kind of the artist became really interested in sort of the process of creation. I'm kind of giving you some of these a bit sort of loose references to point out somehow this relation between, you can have sort of an abstract idea of something, but then this idea needs to be actualized, or through design it can be actualized in different ways, different mediums, and the final outcome is very dependent on the choice of this medium. Or so this is actually a small kind of a project we did with a studio that we have in Zurich. This is done with so-called big gun script. So this is like GAN is a generative adversarial network. So you can, it's like a machine learning model that is generative. So you can sort of generate fake images, and then you can sort of use them to create these hybrids. And then we did like a small project using those. So these are all just directly from the script. So no Photoshop, nothing, of sort of different objects in the environment. And we were kind of trying to get a bit of this architectural kind of feel. And I will show you actually this script probably at the very, very end of the one of the last sessions. We'll play a little bit with these scripts because they're just publicly available. You can also just Google in Big Gun and play with them yourself. And yeah, that's a little bit also to showcase a different way of working, or where the designer doesn't really have a full control of what you're doing, but you're in a way, you're almost like a gardener, or so you're kind of tending to this garden of creation without having maybe a direct influence on how this garden grows. Okay, here's some other examples from my previous work. The top one is it's actually a painting robot. So the robot is just painting, and it's recreating an image by having a brush, and basically you can sort of sample an image, and where you want to have darker areas, you make the robot kind of go a bit lower. So if you have a tracing curve, you make the robot kind of just go lower. You create a bigger, kind of wider area of kind of dark ink, and that creates sort of a darker tone. And where you want to have a lighter area, you make the robot go up. So you make the curve the path just go up a little bit, and then you get sort of you get a lighter area. And if you do this with a fine enough resolution, you can actually recreate any image you want. Or so that's basically a process of printing. Or here it's just done in this sort of automatic way. And then some of the similar sort of concrete formwork prints that we did some already, I guess, 10 years ago. And you can also use something similar to do these sort of light paintings, or where you have a long exposure photography and you're kind of printing in the air with like a small light source, like an LED lamp or something like that. Or so this is just examples of how you can bring this algorithmic design into the real world, or that's kind of where it really becomes interesting. Get it off the screen. Okay. Course topics. So I would like to run you through the topics that we will go through. That's now the final part of this introduction lecture. So the topics that we will go through during this course, and they're kind of grouped in these sort of 5 big groups, and we'll go through them sort of one by one a little bit, even though there's going to be some sort of cross maybe cross play in between. So some topics are kind of belong maybe to multiple of these or to few of these categories, but I kind of try to group them just to give sort of a structure. So we have fundamentals, where we will work with sort of just basically the basis of computation and programming languages and some of the kind of very simple scripts that we can do with very, very little code. Then we'll work with continuous models. And in opposition to that, kind of discrete models. This is also a very rough division that I made that I don't think I will, well, it's a bit hard to argue, so I will not dwell too long on it, but I kind of try to group sort of models that we use in these two big groups. And then this is then a good foundation for doing optimization. So for example, dynamic relaxation will go into there. So some idea of kind of so now when you have this data and this continuous and discrete models, we can perform optimization on these. And then we will end up at the very end with learning kind of the idea of adaptation. So we'll look at some maybe machine learning scripts in a very kind of rough manner, and I'll show you maybe how you can start playing around with those. That's a very, very new field. And basically, as I'm doing this course, this is also kind of developing. It's also part of my ongoing research and my PhD that I'm doing at the moment. So it's kind of just kind of at the very edge. Okay, what are these fundamentals? So object-oriented programming paradigm, specifically in Python. So we'll basically look almost exclusively in Rhino Python programming language. So I'll teach you a bit of Python, even though I'll show you some other workflows as well, which will also be Python-based, but they are just a bit different environments. For that, we'll revisit a little bit of vector math. Not really revisit, but we have to brush up our math skills again, because we'll work a lot with vectors. And then matrices, transformations, a little bit less, but kind of this is sort of implicit in this linear algebra kind of vector field, vector math areas. So then geometry constructions, curves and surfaces. This is mostly related just to how Rhino displays geometry, and then somehow we'll work with randomness a lot. So, okay, so these are some of these examples here. Another example of sort of a digital thinking before computers is from, this is actually an Alberti's project, Descriptio Urbis Rome. And I'll give you some reading at the very end where this project is a bit described by Mario Carpo. So Alberti was looking into how to create like a sort of how to create like a description of a map of Rome. This was before the invention of the printing press in the 15th century, and of course before the invention of computers. So he was interested in how to transmit this, in this sense, cartographic, but sort of like a visual information or image information in a textual form. So created basically like a code that you can use through polar coordinate to kind of create or recreate a map of Rome. So this is in a way example of sort of digital thinking. So how to kind of store information in a sort of digital way, but basically on paper through code. And of course, this is exactly how images are today stored in computer. So they're stored as just kind of a long string that is being recreated on a screen 60 times a second or something like that. Or so Alberti was already kind of thinking about these things. And yeah, then in this fundamental part or fundamental topic, we will be looking at maybe a little bit of kind of graphs, Boolean operations and shapes. So that's also a little bit comes from kind of Rhino modeling, and yeah, some kind of simple sort of curved surfaces, a little bit kind of getting into that. Again, also sort of, it's not really computational thinking, but sort of, geometric thinking between Antoni Gaudi's sort of designs for Sagrada Familia. Yeah, there's also text from Mark Brewery, who is now a lead architect on that project. So he kind of continued Gaudi's work. There are some texts from him also in our collection. Okay, then we'll continue the second kind of big part, which is continuous models. And here we talk about vector fields and kind of particles. attractors, geometry evaluation, so curvature of curves and surfaces, deformations, and for example, metabols, these types of functional surfaces, kind of topography, and maybe kind of fluid dynamics. So these are the topics that we will revisit there. And so, you know, this is the work, for example, from Foster and Partners 21 years ago already. So the Great Court at the British Museum, or so there's basically a kind of formula that describes the surface. So this is a way of parametrizing a surface, or there's a parametric equation that basically describes how the surface looks like. And these are actually some this kind of reaction diffusion models from one author, from one artist here, Jonathan McCage. We'll be looking at these sort of, again, vector fields and sort of flows on these vector fields. And this is one of our projects from kind of one of the AA summer pavilions. This is against like 12 years old. Or so these topics kind of, they work with, or here we kind of work with this, I call them continuous models, because somehow there's maybe an equation that we can sort of use to subsample a space to as fine degree as we want, even though, of course, in the end, you know, these are just discrete particles that travel along the surface. So we cannot really achieve continuity in a computer, but we can sort of define continuity. And then sort of in order to fabricate it or work with it, we need to sort of eventually discretize it. Okay, but in their nature, these models are continuous. Okay, and then another big class are maybe these discrete models. So here we talk about Lindenmayer systems, so L systems, fractals, cellular automata. We'll look into that a lot. Then kind of voxels, so three-dimensional pixels, swarming, shape grammars, not so much, but it's also a big topic here. Subdivision we'll look into, and then of course they're maybe more relevant for architecture. Panelization, tessellation of surfaces, folding, and so on, like origami. These topics kind of fall into there. Okay, this on the bottom left is an example kind of so shape grammars, and some kind of spatial lattice sort of trusses here. Then this is a 2D cellular automata. And then this is on the top left is the Salvador Dali's painting. It's kind of a recursive painting because you have a painting and then you have a small painting of a painting inside here. So it's and it's kind of created again from these pixels. So again, idea of sort of sampling an image kind of comes into this topic as well. Okay, then the fourth big part is optimization. So optimization strategies, topology optimization, we cannot really look too much into that because this code is, this goes like way beyond this course, but we can just kind of look at sort of what is topology optimization. And we will work with much simpler models like dynamic relaxation and minimal surfaces. So this we can do kind of directly in Python and in Rhino, so we will do that. And then we look a little bit of this sort of artificial evolution and genetic algorithms, even though there we also cannot really go too deep because this is a, yeah, we could do a whole course just on that. But I'll maybe show you some codes of how you can kind of, you know, get started with that. I think, yeah, this is basically, you could, in my master's studies in, when I was in Zurich, we had a course that was called The Blind Architect, where we just worked with yeah, genetic algorithms in design, but that was kind of a whole course just on that. Okay. Okay, yeah, so topological optimization, or topology optimization here on the left, related to sort of structural optimization and sort of 3D printing, the fact that we can now, that we can sort of print very complex shapes. Then we look at some of the cellular automata models for this kind of smoothing. It's used in also procedural modeling for example, games and movies. We'll look at some of these, and we'll do this one here. We'll do kind of dynamic relaxation. So that's basically this kind of, we can also do this then hanging chain models sort of in Rhino, kind of from scratch. Again, if you have a Grasshopper script, you can, there's some Grasshopper components that do exactly the same, like for example with Kangaroo, you can do particle spring models, but we'll code it directly from scratch in Python, and you can see a little bit how it looks like. Okay, and then the last part, which we will just, I wouldn't say brush off, but kind of do it as a kind of a just finally at the very end to look at some, advanced topics, learning, or sometimes this is called adaptation. It's also quite an emerging field. So maybe in the last few years or 5 years, there has been quite a kind of explosion in this field, in the field of design. So machine learning kind of started to become mainstream, and then of course permeated all the other fields, including art and design. So here we'll look at a little bit at machine learning, neural networks, variational autoencoders, and generative adversarial networks, or these so-called GANs. And these we cannot really code from scratch, even though they're not really that hard. But we'll work with some already sort of set up models, and I'll show you a little bit kind of how you can start off with that. So this is again big GAN script here on the left, top left, so you can create these sort of image hybrids. And then part of my research that I'm doing, part of my PhD, is using variational autoencoders on three-dimensional like geometry, so three-dimensional kind of wireframe lattices. So I also have now a paper that came out just in December 2020, so 3 months ago, or 2 months ago, basically. And I can maybe give you that paper also, you can have a look at it. You could do something then similar, just sort of with GAN generated floor plans. There are a lot of groups that do that. So, and this is maybe a bit of a fringe example of also quite older one of using the so-called Boltzmann machine learning to recreate sequences. We will not really look into that, but that's maybe just kind of an interesting example that I sort of found. Okay, so there are kind of these topics are also quite new and developing, and I just want to give you a sort of at the very end, I will give you some introduction into these. This is the recommended reading. So the ones on the bottom are already, I mentioned them. So there is this Python for Rhinosaurus. So that's this Rhino Python primer that is in the manuals folder on my courses. And that's basically kind of Rhino, like Python coding in Rhino. And this is excellent reference for you. If you want to go a little bit ahead, you can just go through this document in your own pace, and I will explain many of the concepts from basically this book, my coding sessions. But if you want to get a bit ahead, you can just kind of, feel free to go on. But this is kind of a manual for learning Python in the context of Rhino. Then we will not really work with Grasshopper, or we will not really go too deep into it because it's again a bit separate topic, bit separate workflow. But I also gave you this Grasshopper primer here as well. So if you want to learn more about Grasshopper, this is a great reference. Also, it's basically like a tutorial PDF, and you can just go through it again on your own pace. And this is also great to have in general, sort of outside of this course. So these two are basically tutorials for learning Python in Rhino and Grasshopper. And if you go through these two, which you cannot really do in this course because I think they're way too long, but if you would just go through these two documents, you would already, you might know some things that I don't even know. So, so they're kind of a great reference. Then there's another, so this textbook that I'm kind of preparing, which is not done. That's why there's a small draft here. It's called Mathematical Principles of Computational Design. This you can use again as your own learning reference. So there's many topics that I'll describe in the course are explained here as well. And even the structure, there are parts that have exactly the same structures. There's fundamentals, continuous models, discrete models, optimization, learning. And the structure is still like that. And this was, I kind of concluded this in September last year. And this is a draft version. So I'm still working on it, and I will be working on it for a couple of years more. But you can have a draft version, and I would just ask you to not distribute it further. Yeah, because it's a work in progress. So everything is just draft. But I think it can still be useful for you to learn rather than for me wait to kind of finish it in a few years, and then what's the use of that then for you? So you can use it as a draft version for your own learning if you find it useful. Okay, and then a small text or a good reference to read at this point is the This is a rather short book, The Alphabet and the Algorithm by Mario Carpo. And we have this text in the, again, the readings, it's there. We have, of course, just a scan of one chapter, so it's just a few pages. But the book itself is rather short and it's really nice read. And if you have a chance to get it in the library, do it. Otherwise, you can just kind of go through the text that is in the readings. And here, the Carpo is basically a historian of art, a historian of architecture, but he's kind of looking at this whole kind of history of sort of architecture and design, the architectural design from the, so with that context, and kind of looking at basically really critically at this new technologies. So use of computers, use of kind of computation in design today. So he has this a huge kind of knowledge of kind of history, but is able to kind of create very good parallels to kind of today. And I think it's a great beginning text to start with. Also, some of the ideas that I explained today in the introduction, when I talked, for example, about some references to Alberti and architectural design in general, kind of drawing, these are basically his ideas from this book. So, okay, so that's a text that you can read, and that's it. That's your kind of reading for next time.